risolve. Please.
Should I start? I can start. So welcome to everyone. This is the first lecture of the Algorand, of the International School on Algorand Smart Contracts. My name is Visconti. I'm a professor of computer science, and I'm going to talk about blockchain consensus mechanisms. This is a school that will mainly focus on smart contracts. It's written in the title, and is supported by the Algorand Foundation. All right, so the class is, this lecture is divided mainly in three parts, as you can see from this outline. So in the first part of the lecture, I'll talk about old school consensus mechanisms. That is basically what can be used to build a permissionless blockchain. It's very important to understand what is a blockchain and then where the consensus plays a role. And there can be many definitions. Blockchains is something, it has been proposed in the paper of Nakamoto, and still the definition has been changed a few times. There are several definitions around. There is no official definition. Things are change very quickly in this context. It's still not super mature enough to have a formal definition that is well known and approved by everybody. So I'll give you an informal definition that is relevant for what I will then say during this lecture. So we can consider in this lecture a blockchain as a decentralized computer, despite the name, chain of blockchains, right? So chain of blocks. Just think about a decentralized computer that is publicly running programs. And these programs are usually called smart contracts. And all programs require inputs to then make some operations. And the inputs are received by this computer, not from a keyboard, but from transactions that arrive from the network. And the state of this computer, so at which point is this computer, the values of all variables of all smart contracts that are currently in execution, is uniquely defined by the sequence of transactions executed by this computer from the genesis, basically from the bootstrap. Okay. So think about an abstract computer like the one that is in this picture, if you see in the corner. I'll take a pointer now so that it's easier. All right. So think this decentralized computer as an abstract computer, virtual computer, that is then realized through the work of real computers, many of them. So now the first question is, where is the blockchain stored? Okay. In general, we can, the only requirement is that it is jointly maintained by several computers. It doesn't really mean that the blockchain is everywhere. Maybe every computer can store a piece, right? What is important is that these computers are usually mutually distrustful, which means that they do not belong to the same organization, right? That's one important thing, so that this abstract computer can somehow not be a single point of failure. And now, as I was mentioning, in general, it's possible that the blockchain is stored in many computers, but no single computer stores the full blockchain. Okay, we will, for this lecture, consider, for simplicity, the case that jointly maintained means that there are computers that store a full copy of the blockchain. So then, which means the entire sequence of transactions from the genesis of the blockchain until its current state. Okay, this is not a crazy assumption. This is actually a very concrete assumption, because in deployed blockchains, this is what in general happens. It's not necessarily always the case. There can be, all possible ideas to store the blockchain in a even non-natural way. But if you consider Bitcoin, that is the mother of all blockchains, this is what happens. There are full nodes that are precisely nodes that store the entire sequence of transactions that have been generated from the Genesis block until now. So now that we know that we have all these computers that are storing a sequence of transactions, the main problem is that how do we make sure that they agree on a common state on the same sequence of transactions? Right, so different computers can have different views. And then different views, they define different computers, different abstract computers, so different blockchains. But we want one blockchain, a client, a user of a blockchain of this decentralized computer would like to talk to that one, the unique blockchain that has that name. So how do we make sure that these computers have a common view? And the situation is actually very difficult. This is a difficult question because we must try to achieve this consistency in the presence of faults. And there are various faults that can happen from a simple crash where a computer for some reason is not working anymore. It's not answering anymore to any request on the network. There can be omissions where there is a computer that is answering, but selectively, not to everybody. And there can be, several intermediate states and up to the Byzantine behavior, that is the worst case, which means that a computer that is doing whatever is possible to do, in the sense that it's not necessarily following the protocol, is even playing adversely against the goal of other computers that want to have a common state. So the Byzantine behavior means that that computer is completely out of control, and out of control doesn't mean that does random things, can do things against others. Okay, again, this is really something that is very dynamically changing. Current view of a blockchain can be seen as a sequence of these 3 layers, but again, this is not really very strict and changes very easily. So there is an application layer. It's where the smart contracts are, the programs. That is actually the core of this international school. There is a scalability layer, which means that the programs that one writes for this abstract computer first go to a layer that tries to optimize the performance of the computer, because running many programs can be very expensive, and the scalability layer tries essentially to generate a summary of what all smart contracts are doing, because the summary will be much wider, and then this lighter information is transmitted to the next layer, that is the consensus layer. The consensus layer is the actual moment in which the truth is established, which means what is the current state of the blockchain is decided by the consensus layer. Okay. So the scalability layer is something that 5 years ago didn't appear in any of such pictures. It more recently starts appearing and becomes more and more crucial because more or less all blockchains are suffering from the scalability problem, which means the more the demand is increasing, the more it's problematic for the consensus layer to provide an updated state efficiently. Okay, so let's now that we have defined this school is about this lecture. Sorry, it's about the consensus layer. Okay, so we will focus on this layer, and this is not a new concept. It's not something that was invented by Nakamoto. Actually, already from 82, there was a problem that was defined. That is the Byzantine generals problem. And it's the following problem. So there are some generals that are attacking a fortress and must decide as a group only whether to attack or retreat. Some generals may prefer to attack, others may prefer to retreat. The important thing is that all generals agree on a common decision. Okay, so this is a good example because you can see a case in which either we all do the same thing and the result will be good. If all generals decide to attack all together, probably they can win. They have higher chances to win. If instead only some of them decide to attack, and others don't attack, the very few ones that decide to attack are going to die, right? Because not enough soldiers will be in the battle. So here it's an example where consensus is extremely important. And in this description, all generals can try to propose something, and this is actually called Byzantine agreement. Okay, where is the Byzantine agreement? Where is the Byzantine keyword? Important is that some generals might actually be traitors, might actually work against others. So while generals try to get a common decision, either we attack or we retreat, among them there are some traitors, so Byzantine generals, that they can try to misbehave so that the final outcome for some generals is to attack, while for others is to retreat. And basically they will then have bad consequences. Okay, so this is the Byzantine agreement problem. And if there is only a single general that is proposing the decision for everybody, okay, then this is called actually Byzantine broadcast problem. And this is actually the Byzantine generals problem, was defined in this way. That is just one source, one general that at some point will want to communicate to everyone else the decision, okay? And to communicate this decision to everyone else, there is a problem because there can be traitors along the way, and therefore some of the destinations, some of the generals will receive the message attack, others might receive the message. The problem is, of course, this problem is, of course, connected to what we want to do. This is precisely the reason we need an agreement among all nodes of a blockchain so that they have a common view. It's essential that they are consistent with a unique view. Cryptography will play a role in what we say today. In particular, it played already a role in the past, but very minimal. Essentially, only digital signatures were used in consensus algorithms in the 80s. But with modern blockchains, there is much more advanced cryptography that is used. So we will, during this lecture, introduce some cryptographic tools so that we are all sure that we all understand what they are, what they do. And there is a nice tweet of Itai Abraham that say the cryptography is eating the world, which means, which is at least my interpretation, that whatever you are doing artificial intelligence, you want to do consensus, whatever you're trying to do, you can have brilliant ideas, but then when you want to deploy what you are doing, you will have to face adversaries, and you will have to go through cryptographic tools in order to make it secure. Okay, we start with digital signatures. Probably you all know what it is. Indeed, I'll be very fast on this part. So we have, for a digital signature scheme, we have a key generation algorithm that on input a security parameter, this key length, that essentially means how secure you want your signatures, your signature scheme to be. So the security parameter will tell you a higher security parameter will produce a larger key, and the larger key basically will correspond to harder life for the adversary to attack. The key generation procedure outputs a pair of keys, a public key and a secret key. The secret key is used to sign messages. This signature procedure can even be deterministic, meaning that there is no randomness at all involved. And basically, if you sign 10 times the same message, you get the same signature. It can also be randomized. In a sense, some schemes also provide different signatures of the same message each time you run the algorithm. Clearly, the key generation algorithm is randomized. Of course it is. And the verification procedure takes as input the public key, the message, the signature, and gives in output a bit 0 or 1. Of course, the properties are that if you verify a well-formed signature, the output should be 1. Okay, that's clear. We want security in the sense that no adversary should be able to produce a signature of a new message. New means it means that it has not been signed already by the signer, without knowing the secret. Okay. These are, of course, very informal definitions. In cryptography, we have formal definitions, but it's out of the scope of this lecture to be formal. And signature scheme have an immediate application that you can understand. It's a non-repudiability, the sense that if I'm the owner of a public key, in the sense that I know the corresponding secret key, and at some point I decide to sign a message, and this message appears in the signature somewhere, I cannot deny anymore that I signed it, because no one else could ever sign it. So it must come from me. Okay. Worst case scenario, I mean, the only thing that can save me is I can say, oh, probably somebody managed to get access to my key. I didn't sign. But except these special cases, good luck justifying such special cases in the presence of a judge. Signature schemes achieve no repudiability. When you want to use signature schemes, usually you are required a little bit more infrastructure. In particular, you need a public key infrastructure in order to make a mapping between a public key and the full name of a person, for instance. Otherwise, if we talk only about public keys, a message has been signed by the owner of the secret key corresponding to that public key. That's it. You basically talk about a subject without having an identity. Okay. A public infrastructure, instead, it's an infrastructure that gives you a mapping between public keys and identities. In general, having signatures and public keys, it's useful. It has several applications. In the consensus, you can start making up your mind about the importance of having this tool. The importance, for example, the following. If an adversary wants to, generate two inconsistent messages, sending the first message to a player and another message inconsistent to another player, right? This simple attack without signatures, it can do it, and therefore it's an attack that can make damages. With signatures, basically, it cannot do it anymore. With signatures and the public infrastructure, you cannot do it anymore because the other two players can simply exchange their views, basically all messages and signatures that they have received so far, and they will immediately detect that there is a player, that player with that public key, and in case of a public infrastructure with that name, that is cheating. Okay, this is a bit a jungle, going to different results, papers, and blog posts. You can find different names depending on the context. So sometimes you will find the word authenticated Byzantine agreement or authenticated Byzantine broadcast, referring to the fact that this scheme is using signatures or public or public infrastructure. Okay, so now that we have defined this cryptographic tool that will play an important role, let's see what we want to achieve. We want to achieve the decentralized computer, right? And this was essentially already defined a long time ago. There was already a paper of Lamport, and then also, more in a more explicit way, Schneider in the 90s. Defined the following decentralized computer. So one server, a machine, is split into multiple servers or sharing the same state, so basically realizing the same virtual machine. And this is to prevent faults, even Byzantine faults, which means a corrupted player, somebody that is playing against you. And if we can do that, we are going towards a decentralized system. The difference between distributed and decentralized, it's essentially based on the fact that you might want the system still to belong to the same identity, that just to make sure that a computer is not just captured by someone else who wants to have several machines, okay? So there's one organization controlling everything, then you have a distributed system that, but instead, if it's managed, the governance is in the hands of several organizations, then in this case, we call it a decentralized system because there is no central organization in power. So this state machine replication is what corresponds nowadays to a permissionless blockchain, okay? Where basically what is easy about it? It's easy the fact that you know already how many players are on the table, the players that have the governance, that will have copies of this blockchain, and even their identities, okay? It's known upfront, so when the system starts, you all know this information. You already know this information. Okay, so also the word consensus is used in several different ways. It's used in particular, sometimes just Byzantine agreement, it's called consensus. So that's why here I add ledger consensus to mean state machine replication, to mean again what we want to achieve today, which is a blockchain, a sequence, the state of a blockchain, a sequence of ordered sequence of transactions that is shared among multiple computers. So realizing the state machine replication requires to achieve two main goals. Goal number one, consistency. Honest nodes must have the same view of the state of the machine, which means the same sequence of transactions. Goal number two, liveness. Every valid transaction should at some point be executed and therefore will contribute to the next update of the state of the machine. Notice that it's very important to have also the second condition, otherwise consistency is meaningless because you can have a blockchain that is just doing nothing, okay, zero transactions. So of course, everyone, it's easy to make it consistent because just we don't do anything. But of course, it's useless. We need liveness so that the blockchain is useful. Feel free to write questions in the Q&A session section so that I can, sometimes I give a look and if there is something relevant, I will answer it immediately on the fly. If instead I don't think it's a good idea to answer, I'll just postpone the answer. Maybe at some point we'll have a break and we can discuss offline about it. So we reached at least an intuition about what permissioned blockchain is. There is a known governance, and there are nodes that are well identified that maintain the full list of transactions. How do we construct it? Okay, this is the next step. So let's start, in a setting that is very simple. Okay, let's assume we are in the synchronous model. I'll tell you in a second what this model is. And we are without adversaries, okay? How do we solve the problem? Still, there can be a crash of the computer, of course, right? So how do we solve this problem? Okay, it's not complicated. We have several nodes, right? The idea is just to have a rotating leaders. There is time t, one leader, time t plus one, another leader, time t plus two, another leader. So each time a node is a leader, it will announce the next block of transactions. Okay, so this announcing this block of transactions, this will reach all other nodes that will update the list, and everyone is happy. Everyone maintains a consistent list with others. It's you can check your own as an exercise. You trivially get consistency and liveness, both properties. Okay. Okay, what is the synchronous model? Synchronous model is a model in which we are assuming that all computers actually have a global clock, pretty much synchronized. Because I was telling you, at time t, one node will speak, time t plus one, another node will speak. So they must agree on what is t and what is t plus one, right? So they must be synchronized. Of course, in this setting, things become easy to do because you can know at any time what another node is expected to do because it's time 3 plus 7. You know already which node should do something because it's written in the protocol. And the message, it's the assumption that it's a message that is sent during time t is delivered by timestamp t+1. Okay, that's why it's a synchronous model. Things proceed according to some specific bounds. This might be excessive, right? So it's a model that, probably you can realize it even safely in at home with a local area network, right? Where you control everything, right? It makes sense. It's not a crazy model. You can actually have this type of consistency, but it's not really clear that this can match reality on the internet when you have computers all over the world with different type of connections and computers belonging to different organizations with different performance. In particular, such computers that can be distributed all over the world can be also under attack. So, and when a computer is under attack, it's not really clear I can do all my duties, all my tasks in between time t and t+1 because I'm under attack. Correct. So this is the basically starting point, okay? So we can have a permissionless blockchain and it's easy to construct for now, still without adversaries, right? Just to tolerate faults, but in the synchronous model, this is very easy. Okay, next step, because we know there are adversaries, right? So we must kind of admit there might be a node that at time t will actually start messing up things. You know, it's not his turn, for instance, to propose a block, but he will propose it. Or when it's his turn to propose a block, he will not. He will send different inconsistent information to the other, right? So there's various ways to misbehave here, and actually, by just notice that by just in the previous approach with the rotating leaders, by just implementing appropriately the step in which a node is a leader and will announce the next block, okay? By implementing it with a Byzantine broadcast, you actually still get a permissioned blockchain in the presence of Byzantine. Okay? What is a Byzantine broadcast? It's a way that I announce a message to others, and even though there are adversaries in the system, all honest players, this is the first property of Byzantine broadcast agreement, honest nodes will get the same message, the same output. Okay? This property of the Byzantine broadcast will help us in having consistency of our state machine, right? I recall you that we want to build this decentralized computer, state machine replication, ledger consensus. This is our target. And we need to achieve these two properties, consistency and liveness, okay? So I just told you that there is an approach, this one, that works in the synchronous model, very simple, but without adversaries. And again, the same approach will still work with adversaries if you use Byzantine broadcast to announce your next block. Okay, Byzantine broadcast, it's a protocol that guarantees in the presence of adversaries agreement so that honest nodes will get the same output, and this is useful to get the consistency property, number one. And then there is a second property of Byzantine broadcast, it is validity. Validity means that if the sender is honest and runs the program, the procedure with the input M, then the honest node actually will get precisely M, okay? And this will be useful to get liveness, okay? Good, so for now, we know how to build a decentralized computer in the permissioned setting if we have a Byzantine broadcast protocol. How do we get to Byzantine broadcast protocol? It's not that difficult. Okay, about Byzantine broadcast, there is also a termination condition, but for simplicity, I'm omitting it. There is, for instance, for whoever will be interested in knowing more. Of course, I mean in this lecture, you will not know everything about consensus. It's clear, right? But I mean, I'm giving you an high-level overview of how it works, and then I'll give you also references. I will cite also papers so that you can figure out on your own the details that you are getting. Okay. So, in particular, for instance, there is a work of an old work of Dolev and Strong from '83 that shows how to have a Byzantine broadcast protocol. in the setting that is permissioned PKI and it's synchronous. Okay, so in this setting, and the protocol of Dolev and Strong, it's actually an easy protocol to understand. So it's something approachable, right? So tomorrow you can devote a couple of hours to read this paper, and you will see that you can understand how it works. It's not difficult at all. What is one property that is interesting in this protocol is that it works for any number of faulty nodes. Okay, this means that we are not assuming that there is just one adversary or three adversaries or 10% of the players are corrupt. No, any number can be corrupt. Even a majority of the players can be corrupt. Okay? I'm just stressing this fact because everything else I say today and what probably would expect that requires always some honest majority. But this protocol of the Dolev instead it works and achieves within the broadcast in that setting with those restrictions, of course, regardless of the number of corruptions. When you might wonder now what happens when you realize the decentralized computer, therefore having several nodes, rotating leaders, announcing their block with the Dolev-Strong protocol. If you have also now a decentralized computer that is secure against an unlimited number of corruptions. Okay, and that will be too good to be true. It will not be true for the following reason. If there is a decentralized computer and I'm a client and a user, somebody that would like to use this computer, right? I want to send a transaction from outside. I'm not part of the governance. Okay? How do I check what is the computer, the state of the computer? I have to ask. But if there is a dishonest majority in the governance, okay, I will never figure out what is the real state of the computer, even though inside the governance, there are a few nodes, the only honest ones, the ones that are proud of themselves, didn't give up, they are honest, and they are all consistent on a given view. Okay, there is that given view, but it's justified only by very few players that can sign and say, yeah, this is the right one. There are at the same time many malicious players that will show, no, there is this other view, signing it, and there is many of them. Therefore, from outside, you cannot just, it's impossible to have a blockchain decentralized that can be secure with dishonest majority. This is impossible. You need honest majority at least, okay? So when you apply the Dolev-Strong protocol inside this idea of having rotating leaders, you get a decentralized computer, you get ledger consensus, but it will work just with the assumption of just honest majority. You don't need 2/3 honest majority, just honest majority. So the liveness guarantee, I want to recall you, the liveness guarantee is extremely important because the liveness guarantee says that this computer works, it's not stuck. If somebody proposes a transaction, a client, the transaction soon or later will be executed. So it's an input, a transaction for a smart contract. The state of the smart contract and therefore of the decentralized computer will be updated. This is liveness, it's extremely important. Okay, so in this construction of a decentralized computer that can work just assuming honest majority, as you can see here, follow my pointer, I am assuming a synchronous model. So these computers should be, at least the honest ones should be in sync. So the clock should be essentially aligned and the delivery of messages should be extremely fast. This result needs signatures and public infrastructure. And if we remove public infrastructure, then we cannot get such a beautiful result. It has been proven by Pease and others that you need at least the adversary should be below the 1/3 threshold. So no more than 1/3 of the nodes. So less than 1/3 of the nodes can be corrupted in order to realize ledger consensus without signatures, without public infrastructure. Okay, very good. So we can recap. We have already, starting from zero, we already understand something. Realizing a blockchain, a decentralized computer with a governance. Permissioned setting means with a governance that consists of very well-known actors. You know the number, you know who they are. It's easy. To realize it, you need to achieve two properties, consistency and liveness. And you just can have a rotating leaders and use Byzantine broadcast. That it's a sub-protocol that satisfies agreement and validity that are two properties important to get ledger consensus. And rotating leaders plus Byzantine broadcast, you can take the less strong result. If you are in the synchronous model and you are using, of course, you are in a setting that is permissioned, they use public infrastructure, you get a decentralized computer that works with RSA. Perfect. Any questions so far? I mean, feel free to write more questions in the Q&A. As you have seen, I mean, sometimes I have a look at this bulletin board, and I will and I answer. All right, so this was a very good, first part in the sense that the problem doesn't look very difficult, right? We are already, the only black box in what I say so far is this DOLEF strong protocol, and I told you it's not that difficult. It's not even that difficult, and there are also other protocols. There are many boxes, black boxes, like also the signature scheme. I didn't tell you how it works, right? But you believe there exists such a scheme, because we use them continuously. But for sure, now we have a goal, right? What is now bothering more, at least the first thing that is bothering, is this synchronous model, because I might want to basically move from a distributed setting to a decentralized setting. When I do, this jump, it's not clear anymore that all computers share the same clock and all messages sent among them are sent very, very efficiently, right? The moment it's decentralized, it basically becomes more difficult to have such guarantees. Okay, so one direction is to go to the full asynchronous model. Say, okay, so let's not guarantee anything. Okay, can we realize a decentralized computer in this setting where even permissioned, where there is no basically guarantee about the clocks of the players and no guarantee about how much time a message takes from the sender to reach the receiver, right? Okay, so you can, this will be great because it will give you applicability to any scenario. Even the broken internet is a place where you can run such protocols, right? Internet under attack will be fine. Unfortunately, this is not a direction where we can go. It's this setting, it's so limited in what it gives to us that basically there are impossibility results, or whenever something is not impossible, it's anyway very hard to do in the sense that it's very inefficient, and therefore we have to look at something else. Okay? There is this impossibility, for instance, of deterministic Byzantine agreement, even with just one crashing node. So no Byzantine adversary, just a node that crashes. Okay, and you cannot do Byzantine deterministic. So this is due because in this setting it's basically impossible to distinguish a crash, basically a node that will not respond anymore, okay, from actually a node that actually responded, but just message takes you know how much time it takes to reach, right? So since you cannot distinguish the two cases, it's very tough to construct protocols in this setting. There are impossibility results and even other results that are not impossible. They provide positive results that unfortunately are not practical or efficient enough for the concrete scenarios. Okay, so we are, with good news in the synchronous model, terrible news in the asynchronous model. Now we have a natural question. Yes, can we do something that is at least in the middle? So something where we can get positive results that are useful and practical, and still we are not relying on unbroken, fully functioning internet, right? And shared global clock. That is really too much. So there are good news. There is a work that's from '88 that defined the partially synchronous model. And in this model, we assume that in general, okay, so basically when nobody is under attack and there is health in the network, everything is behaving correctly like in the synchronous model. But then because of the denial of service attack or various other reasons, there is a crash or whatever, there is a time window in which the network is unreliable, where the synchronicity assumption does not. Okay, this is the partially. And in this model that was proposed by the work et al., they showed in this model that is realistic. Okay, this corresponds actually to the internet. In this model, you can manage to get consistency aliveness. So a protocol that gives you consistency aliveness, which means you realize the decentralized computer during those time windows in which the network behaves well and the computers are not under attack. Okay, when there is good sync, you get everything. At the same time, when the situation becomes complicated, there is an attack. The internet is partitioned in 4, right? So something really devastating. Consistency is still preserved, okay? That is extremely important. It means nobody can tamper on this abstract computer, even if the network does not work for a day, a week, okay? It's very important. Of course, when there is poor sync, you don't get liveness, which means, okay, during those times, during tough times in which there are issues, the computer is a computer. It's like when you are using Windows and Windows does sometimes, it's blocked, right? So during that time, transactions will not really be accepted, okay? So, I mean, it's not really zero liveness, it's just that you don't have a liveness guarantee in the time window in which there are attacks, okay? Which is very reasonable. You are under attack, things are suspended for a while, right? It's very reasonable. So this is actually something that makes sense. We can build really important infrastructures in this partially synchronous model, and this infrastructure can run on the internet. If we prove that the way we realize them is secure in the partially synchronous model. Okay, what is very interesting is that everything I say so far was about, long time ago. But Nakamoto, which is what happened more recently, had the brilliant idea. One of the brilliant ideas of Nakamoto was to actually consider the case in which during poor sync, while the network is under attack, actually it makes sense. You cannot have consistency aliveness, both of them, because it's too much. There are those impossibility results that I told you, or even in case it's possible, it will be extremely inefficient to get something reasonable. But what is important is that Nakamoto considered the case of having liveness instead of consistency while the network gives very limited guarantees. And these are some consequences that we'll see. Okay. We will have some breaks, I guess, too, because this lecture is divided in 3 parts, so it makes sense to stop after part 1 and then stop again after part 2. And we are close to the end of part 1, so don't worry, don't give up if you feel tired. Don't give up that soon there will be a break. And actually, before a break, I'd like also to have maybe an offline discussion, because I'm sure you are accumulating more questions that you are not writing here in the Q&A in a section. And I'll be happy to discuss them. Okay. Right. So, what is an intuition of? Okay, there is a result of DLS always, the same paper that proposed this model. It showed that, look, in this model, there are good results that we can achieve. But the adversary must be under the 1/3 threshold. Okay? So the adversary cannot have controlled 40% of the nodes of this permissioned blockchain. Cannot. Otherwise, there is no consistency. Okay? Let me give you an idea about this bound, because it's actually the intuition is very simple. Okay? The point is that if you have T corrupted nodes, right, the honest node cannot wait for more than n-T messages, right? Because those T corrupted nodes might not send at all their messages. Right? So a honest node must proceed anyway after n-T messages, right? But if you proceed only having in your hands n-T messages, you must take into account the possibility that out of these n-T messages, T of them could come from the adversary itself, okay? And that's what is the trivial conclusion? The trivial conclusion is that if T, for some reason, the adversary will control more than 1/3 of the players, right? T greater than or equal to n/3. So we have that in the end, a honest player receives less messages from honest players than from dishonest players, right? And you can now have an intuition that things are going to mess up, okay? So that's the reason why, and this is true only for this argument holds until only if T is greater or equal to n/3. If T is below that threshold, then this argument does not work, and actually you can construct protocols, and indeed there are several constructions that can satisfy these nice properties: consistency and liveness when there is good sync, and just consistency when there is good sync. There are several constructions. Okay, yeah, that is indeed the next slide. These constructions are now in the family of BFT protocol, BFT style protocol. There are many proposals, in the years, many optimizations. So a BFT protocol for consensus using, the common language is such type of protocol. It works in the partially synchronous model and can realize the decentralized computer, so ledger consensus, when the adversary is below this threshold in the permissioned setting, okay? Which means the governance is restricted to some well-known entities. All right, so we now know pretty much a lot about the permissioned setting. A permissioned blockchain can be seen as a table where some organizations, mutually distrustful, meet to say we need to offer this service to the community. Okay, so let's, of course, we trust kind of each other in the sense that we know I hate you, maybe you hate me, but I'm sure that it's impossible that 1/3 of us will try to cheat the others. Okay, so that's the basic trust assumption. And this can realize a blockchain without a waste of energy. Everything is pretty efficient. It's pretty strong consistency and fast transactions. So because strong consistency, because you have consistency always, regardless of the state of the network. And you have fast transactions, and so therefore good liveness if the network is not under attack. It's a very good result. And indeed, I mean, you might be aware that even central banks are now considering to move towards a central bank digital currency, and out of the possible options, they are also considering the use of a permissioned blockchain to realize it. Even the Euro Central Bank, it's looking at this direction, not sure it will finally decide to go for this direction, but it's considering this direction. All right, so this is a good moment to finish part 1. Let's stop the recording. Post the recording. Okay, so congratulations, you survived to part 1. Let's now start with part 2. You have now an idea what a permissioned blockchain is and how it can be constructed. Let's see what is the gift that Nakamoto gave us. So going from permissioned to permissionless blockchain. Hey, is it possible at all? So what is they call permissioned blockchain? You know the nodes that are in power, that have the governance, right? And in the permissionless, while in the permissioned blockchain, you will not have this information. So you don't know who keeps a copy of the blockchain, who is participating in storing a copy of the blockchain, who is participating in the consensus. Let's recall what was the trivial solution for the permission model, in particular in the Synchronous model for permission blockchain, rotating leaders announcing a block. Okay, so this simple, we started with this simple construction, right, in the permissionless setting. But if you look at it in the permissionless setting, where you don't have, there is nothing you can do really. The above approach fails spectacularly. You have nothing about that. Because rotating leaders, who are these leaders? We don't know anybody participating in this system. Who is the leader? And how do we define the first one, the second one, the third one? Nothing is certified. There is no closed governance. And people in particular don't want to be permanently connected to the network. That is something said that in a permissionless blockchain must be done by computers that have the governance. Okay, so if you are if there exists a permissionless blockchain, there is some noise. Okay, in the permissionless setting, basically, you have none of those useful advantages. Okay, so it's not clear at all that you can achieve such results in the permissionless setting. Right? Here again, who is next leader? And if so, therefore, more people can propose themselves as leaders. And then how do you, if they propose and they can propose conflicting transactions, how do you choose which one is a good one, which one to discard? And how do I make sure that my selection is consistent with one of another honest user that maybe because of delays sees something else? In particular, there is not even a vote that we can try to run where I say, oh, I've seen this message and I would like this to be the state and I vote for it, right? And maybe we then apply, everyone does it and we apply an honest majority argument, right? That can be an idea. It's an idea that cannot work at all in the permissionless setting. Why? Because I am nobody, there is no PKI here. So when I say I vote for what I'm saying, I have just a public key, but it's an anonymous public key, it's not connected to my name, where I'm saying, I vote for this. Okay, it's an anonymous public key. So the adversary can generate as many anonymous public key wants, right? Because there is, so basically can simulate any number of users, of citizens, and can vote, can have random control of the vote. So eventually, basically, this vote has nothing useful for us because it's there is no concept of majority because it's fully controlled by the adversary that will have easily the majority if he wants so. So this is a typical attack, the Sybil attack, in which the adversary is trying to clone himself. And in the previous approach, the one permissioned, this is a trivial attack. Why? Because in the permissioned, the approach to construct this decentralized ledger in the permissionless setting, when we move it to the permissionless setting, we still would like to have this approach with rotating leaders signing a message, right? Just a signature generating an identity, right, and signing is something cheap. It's easy, very efficient to do, and the adversary can do it massively. Okay, that's the Sybil attack, therefore controlling the majority. So this approach, that is the traditional approach of permissionless blockchain, allows to reach a result only when you have one person, one vote, and therefore you have, and you know in advance that you have a limited number of votes, right? Therefore majority makes sense. But the moment you switch to the permissionless setting, this does not make any sense because of the Sybil attack. And therefore, even though we had those beautiful results in the 80s that were in the permissionless setting, nothing much happened in the permissionless setting until 2008, right? So we had basically all these professors, that researchers that produced those results, that essentially they gave up because the feeling was that it's just impossible. Okay? Just a second. But Nakamoto gave us new ideas and actually proposed a way to achieve a decentralized computer in the permission setting with his paper in 2008. Okay, there are some more cryptographic tools and several ideas. Let's overview what we need very quickly. So now I need to introduce the concept of a collision-resistant hash function. So a collision-resistant hash function, it's a hash function in the sense that you evaluate an input and you get an output. The output is shorter than the input, so it's compressing. And the fact that it's compressing means easily there are collisions, because basically there is more space in the input than in the output. So there exists collisions for sure. But even though there is collision, and maybe there is many collisions, it is hard to find even a single collision. To find what is a collision, two elements in the domain that you give in input to H, such that the output is identical. Okay? That's why they are called collision resistant, because it's hard to find collisions. By hard, we mean nobody can find even a single collision. Okay? Having bounded resources. And in the real world, we use these gadgets all the time. They were used way before Nakamoto. They are inside HTTPS TLS, so they were used already in the 90s. Currently, a standard collision-resistant hash function is SHA-256. You can provide as input a string of arbitrary length, and you get in output 256 bits. So clearly there is a huge amount there are infinite collisions. There are infinite collisions, and nobody can find a single collision. Okay, then building on top of this concept of collision-resistant hash function, it's possible to construct something called parameterized puzzle. What is it? So let's start with the random string, rand. And we can define a set Z such that the size Z of Z is the difficulty parameter of this puzzle. That's why it's a parameterized puzzle. There is difficulty parameter that is the size of a set Z. If Z is small, there is high difficulty. If the Z is big, then you are decreasing the difficulty. How do we construct the puzzle with this idea? The puzzle is the following, very simple. Take H, that is, let's say, a cryptographic hash function, which means collision-resistant hash function with some abuse that I will discuss soon. And the goal is find X such that when you evaluate rand, it is a random string concatenated with X, you get an output that belongs to the set Z. Okay? So this is a puzzle because you have to find X, right? So there is a work for you to do that. But once you find it, it's very trivial for everyone to verify that you actually have resolved the puzzle because you have found such X, okay? Because verification is just an execution of the hash function, that they are designed to be extremely fast. And now you can also understand that if Z is a small set, this is difficult. If Z is a large set, this is easy. Okay, in order to realize this parameterized puzzle, we need H not only to be a collision-resistant hash function. Because why? Because somebody could study the hash function and find a shortcut, a way to quickly find such X, right? So basically the puzzle, even though it's parameterized, to be very difficult. But somebody will study it, it means a small set Z, capital Z, okay? Somebody can still find a shortcut to very easily find an X such that the puzzle is resolved in theory, right? Just collision resistance does not prevent that somebody could find such a shortcut. And we need therefore to assume the hash function to behave like a random oracle. Random oracle means basically you have no idea how the hash function behaves. You just evaluate it and you see it out. So there is no way to find a shortcut because you have no idea about what it does. Okay? Right. So good. That's the first thing I want to introduce: collision resistance function and their use to construct parameterized puzzles. Okay. So now that we have this tool, we can also try to imagine the hash function as a way to get a pointer. How? So when we have a big information, large information x, and we evaluate h of x, we get y. That is a very small information. You can think that y represents x. Why? Because it's collision resistant. There will be nobody will ever be able to find an x prime that is justified with the same y, right? So once you basically compute y, you are blocking x. So y is a short representation of x. And therefore, you can think at y like a pointer to x, okay, intuitively. If you, y, it's a reference that to a larger information, and that's only that possibility. There is no x prime that can correspond to y because nobody can find it. All right. So once you have this idea of using the hash function as a pointer, you can start having a block of transactions, right? X1, it's a block of transactions. And then you can have more transactions, so a block X2, and you can connect this block of new transaction to the previous block of transaction. How? Adding to this block X2 also a pointer to the block X1. Okay? And the pointer is implemented using the hash function. So Y1 is the hash of this block. Okay? You can continue. So you can have one more block of after a month, after a day, after a second. You have another block of transactions X3. You can connect it. So you can extend your data structure. You can connect to the previous block again with Y2. That's going to be the hash of the entire previous block. So Y1 concatenated with X2. Okay. You can continue and continue and continue. And in the end, you have Y5. Okay. Y5 is a short representation of the entire list of blocks. Why? Why so? Because actually, if you modify a single bit of the first block or of the second block, of any block that is in this list, this will impact on a new Y5. So that's why Y5 is representing exactly all this information. Even though Y5 is a small, short information, it fixes basically all the information from X1 to X5. There is no way to change a single bit in these blocks to then still get Y5 as a good representation of those blocks. Okay? This comes from the collision resistance of hash function. Okay. And this is the idea that Nakamoto had in mind to have these blocks of transactions that will altogether represent the state of the computer, right? But there is much more to say before this can work, so stay tuned. So the setting of Nakamoto was extremely complicated because Nakamoto decided not to basically be in the hardest possible situation. A peer-to-peer network, basically without structure. So you don't want to basically have a servers that you can access because servers, can be unreliable. And he wanted a system that works always. So Nakamoto decided to design a decentralized computer on top of a peer-to-peer network. And the peer-to-peer network is open, it's anonymous and open to everybody. Okay. Therefore, it's the extreme point that is, the farthest possible point from the permissionless set. This is completely without structure. You don't know anything. Nodes can be offline, can misbehave, channel are reliable, no common. Okay, all right. But I mean, either I was saying only bullshit during the first part, or we still have a big problem, the consensus. So where are the copies of these blocks with transactions? Who is storing them, and how do we make sure that those copies that are around are consistent, that we have the same sequence of transactions, therefore we are realizing the same abstract virtual computer. Because, you know, seems that strong coordination is required to solve these problems, but we are in the peer-to-peer setting where there is no coordination at all. So it's very, how do you do that? Okay. So let's recall the requirements. We want all nodes to have the same value. This is the consistency, right? We want to see the same information. And we want liveness. We want, eventually, if somebody proposes something, cannot be discarded if it's valid. If it's valid, it should be accepted eventually. All right, so if we have these blocks, right, of transactions, so the consensus problem basically boils down to what is going to be the next block. You can always start from a genesis block, right, by induction. So we have a past history and we agree on it, because this can just be the genesis block, the first block, right? So we agree on something that happened in the past. The question is how this computer can be alive and continue and add blocks so that we all agree, right? This is the main problem. So in this example, you see 4 players, and apparently the input of Ivan, Max, and Jenny, it's the same. It's a set of transaction that is called transaction 2, while Bob has a different input, because from the network he has seen different transactions. He would like to propose transaction 1, right? So one important observation of Nakamoto is that, look, even if you are in this situation, don't think that they should now start to vote and decide that there is more support for transaction 2, and therefore some transaction 2 should be there. The idea is that the main important thing is that we agreement, okay? There is consistency. So it's too much to try to find what is the most desired solution. We are all fine if just transaction 1 is added, as long as we all agree on it, okay? So that's one observation that is very important. It's different from a meeting that you have with your colleagues. When you have a meeting with your colleagues, you have to decide to the restaurant, right? For the day, you say, well, I propose this. I say, oh, I like it. Basically, you do majority, right? Okay, it's very natural, but this brings you to a protocol that is too expensive to be run on a peer-to-peer anonymous network, okay? Too demanding. The idea of Nakamoto is that no, let's not go in this direction when we try to vote. No, let's try to find something more concrete. And the breakthrough of Nakamoto was to switch from the idea of one person, one vote, that, as I mentioned before, makes no sense in the permissionless setting because of the Sybil attack, to the idea of one computation, one ticket. So there is a lottery here now. Not an election, but there is a lottery. So the idea of Nakamoto is, let's have computations to measure the amount of entities participating in the system. Okay, so an entity doesn't count one; it counts for how many computations it can do. And the idea is that these computations should essentially produce tickets of a lottery, so that somebody can claim I won the lottery. So now we could go back to the previous problem. How do we organize a lottery with n players? Maybe we are wasting time. A lottery with n players can be in a peer-to-peer network with any number of players, not with n players. Right? So a lottery in such a setting can be extremely complicated to construct. So maybe it's even worse than consensus. Right? So what are we doing? The intuition of Nakamoto is to have a lottery in the sense of having tickets that are like scratch cards. So once you have a ticket, you know immediately, without talking to anybody, if you won or not. Okay. So what is this is the great idea. So in this way, basically, nobody has to talk to others. Only the winner of the lottery will announce it along with these transactions, and that's why you can get the block that is up. Now the question is, how do you realize this ticket that is a scratch card in a setting like the one peer-to-peer. How do you do it? And Nakamoto had this brilliant idea of realizing this scratch card using the parameterized puzzle. So the computation that I have to do to get a ticket is an attempt on a new X. So I pick a new X and then make an evaluation of H here, okay? This is a computation and then basically a ticket that I have consumed. And now I can check, did I win or not? I look at the output of this computation. I see the first 70 bits are 0 or not. If they are all 0, I won. If they are not, I didn't win. I have to continue. New ticket, new competition. Okay. So this X that must be found is the solution of this puzzle. What are A and B prime? A is the previous block, right? Because I want to win a lottery to add a new block on top of a previous block. So A is the previous block. And if I win the lottery, I'm proposing transactions, right? And these transactions that I'm proposing, they are in B prime. B prime is the new transaction that I'm proposing essentially. And very important, these transactions, B prime, cannot be changed. Okay, follow me on this. It's important also for what I will say later. These transactions in B prime cannot be changed after the fact. This means that I cannot win the lottery and then I decide which transaction to put. Okay? This is important because I could be bribed otherwise, or maybe I'm happy to be bribed, but this basically introduces deviation if I can decide the transaction later, right? While instead, when I'm nobody knows me, I'm trying and trying, okay, I found the solution, and now that I'm stuck with those transactions, I cannot change them anymore. Also, another reason why it's essential that the transactions are blocked there is that among these transactions, there is also the so-called Coinbase transaction in Bitcoin, at least. It's the transaction that allows the winner of this lottery, that is called the miner, to cash a reward. Okay, it's very important because otherwise, if this could be changed, when I announce my winning ticket, somebody along the way could decide to cash, taking my solution of the puzzle, could decide to cash the reward for by himself, taking my money, right? But actually, nothing can be changed in this set B prime. And again, it's the ideas. There are many ideas from Nakamoto to achieve this decentralized computer. Many brilliant ideas. One more is that there must be rewards because rewards will attract honest computational power. You will have people that will just try to win the lottery because it's convenient, and this will attract honest computational power that will make the adversary in trouble. Why? You recall the problem of an adversary getting the majority through a Sybil attack, right? In the case of a permissionless blockchain, those protocols, if you apply them in the permissionless setting, it's a very big problem. Why? Because in that case, it's just a key generation and signatures, and the adversary can do many of them. It's cheap to do that, okay? to run these procedures. In this case, instead, this is not cheap at all. If the adversary wants to win always the lottery or very, very often the lottery, he needs tickets. He needs, therefore, to perform computation. Therefore, if he wants to win much more than all the honest players, he needs more computational power of those players. And this is extremely expensive, okay? It's not cheap at all. All right, so this is a summary of the great ideas that Nakamoto had. Okay, so from one person to one vote, to one computation, one ticket. Look, no reason to talk to others while scratching cards. That's fantastic, because otherwise it would be very complicated to figure out how to realize it. Players have only to make computations. This is called proof of work, this attempt to resolve the puzzle, find the solution. And these incentives are very beneficial. If the adversary has less than half of the global computational power, which is basically the hash rate, how many evaluation of the hash function you can do, the adversary is going not to be able to damage the consistency of this system. Okay, let's review these key steps, therefore. So clients have transactions, right? So I'm a client. I'm not even part of the governance, so I'm not interested in doing this mining of solving the puzzle, but I want to use the computer. So I send the transaction. This is broadcasting the peer-to-peer network. Therefore, there are nodes that are in the governance. They receive these requests of transactions, and they prepare a block, and they scratch cards. So these nodes in the gray box here, they are actually doing the work, the hard work. They are the miners. One of them at some point wins, maybe more nodes will win. Okay, but there will be a winner. A winner will announce the block. Once it's announced, everyone, I mean, the honest players will verify it's well done and the solution is correct. Congratulations. These are the transactions. Okay, I will add the transaction. So as you can see now, there is also consistency because everyone is adding this set of transactions. Okay, and then the hash of the added block will be part of the next block. I mean, whoever wants to add another block now will have to use this new block as previous block. That's the point. And there is a point. I told you there can be, of course, more winners because it's a lottery, and I mean, there are more solutions to the puzzle. So I'll find one, another one will find another one. It's fairly possible. And then we have to decide what to do in this case, because if there are five winners, there are 5 next blocks. Which one should I add? The rule of Nakamoto is the longest chain rule. So you add the block that you heard first. If you are hearing about just a new block, everyone is proposing a new block, you take the one that arrived first to your computer. That's it, simple. But if instead there are proposals of a new block, but you hear about a sequence of 3 new blocks, so a longer chain, okay, that can be added to your current chain, you should go for that option. Okay? Always follow the longest chain. Okay? All in case, in case of tie, then stay with one you heard first. That's the rule that Nakamoto proposed. Okay, it is crucial to start with the public setup, otherwise we are adding what, right? So there is a Genesis block that is must be fixed in advance, and then the system starts, of course. Otherwise, what are we adding the first time, right? Of course, everything is public, so everyone can check in this Genesis block. This is a link to check the Genesis block. And if you go there and check, you can find also the only transaction you see that is in this block. You can click on it and you can see the content of the transaction that assigned 50 Bitcoins to Nakamoto. And in this transaction, there is a field that is free. I mean, every miner basically has a free room to write whatever he wants. And it's because this is a special transaction, one that assigns money to the miner. It's called the Coinbase Transaction. And here, Nakamoto, in this first transaction, in the first block of the Bitcoin blockchain, it's January 3rd, 2009, he added this information, and you can decode this information with this command on Linux, on Ubuntu, or you can go online and use this website. In both cases, you get exactly or more or less this message. So Nakamoto encoded in the Genesis block a message that obviously he could not control, right? He just read it from the newspaper. And this was essential for the security of the blockchain, because this is a guarantee that nobody started mining in advance. Okay? Why is it important? Because I was telling you, the adversary will not have the capability of generating many blocks because he doesn't have enough computational power. But what if he started 3 years in advance? What if he started 1 year in advance? So even with limited computational power, if you start, in advance, if you want to run a marathon and you start with 1 hour before the others, even though you are not well trained, you're going to win, right? So Nakamoto, in the setup of the system, that is the Genesis block, encoded this message, and this is a guarantee, basically, whatever anyone have done, could possibly do before January 3rd, 2009, was useless work because you have now to do the mining starting from this information. All right. No questions? Okay. Okay. Of course.
Even perhaps I have something.
Sure.
To an observation, not a real question. I think that one important point to highlight of Nakamoto consensus is that since it requires a huge consumption of power, it really requires that rewards compensate for this consumption.
Absolutely.
So, this kind of blockchain must implement a cryptocurrency through which to give the rewards to the miners.
Right.
Just to say that
yes.
this is not this is related to the power consumption. But if you have another protocol that is based not of computational power but on stake, for instance, then this motivation is not so strong.
Absolutely, great point. So when here I mentioned that there are rewards for the winner, I mean, the reward, how do you give a reward, right? It's not a check that you get in your mailbox or a wire transfer to your bank. The rewards comes inside the blockchain, and it was, in particular, I've shown you the miner originally was getting 50 Bitcoins. So you need, as Massimo correctly was mentioning, you need an underlying cryptocurrency so that you are rewarded through units of this cryptocurrency. Where is the number 50? That must be here. Okay, it's here. You can see on the bottom right, 50 Bitcoins. And yeah, even here there is 50. So it is correct. It's good, great point. So with this type, with Nakamoto blockchain, where there is proof of work to participate to the generation of a new block, it is required for sure that there is an underlying cryptocurrency so that you can get a proper reward. And it's economically convenient to continue this mining activity. Great point, thanks. Okay, so basically lottery with proof of work and longest chain rule for consistency. And there are, let's see why consistency works. No? Okay, as an example. So here I have a sequence of transactions. There is basically a Bitcoin that is transferred from Ivan to Jenny, then from Jenny to Bob here, right? And now there is Bob, and you can imagine this as it's a first block in the blockchain. This is after a while, this second block. Then after a while, Bob could play a game trying to pay with the same unit XYZ and try to pay two different wallets, two different receivers. Okay, so one is Amazon, another is a bank, and what can happen is that if there is no common view of the blockchain, you might have part of the world, including the bank, that will see only 1, 2, 3. By seeing only 1, 2, 3, the bank will be happy. Say, oh, okay, you're giving me the money, I'm happy. But also Amazon will see 1, 2, 4 only. And by observing only these 3 blocks, 1, 2, 4, say, oh, okay, you give money to me. Thank you very much. But Bob, in this case, is using the same money to pay 2, right? It's exploiting with this attack that is called double spending. It's exploiting a possible inconsistency of this chain of blocks. Okay? And this is this fact that the chain is splitting. You know, it's a chain until block 2, and then it splits into block 3 and block 4, as in this picture, as you can see. It's called fork. Okay. Very good. So this is possible. It is a mess. It is scary, but fortunately, these forks are only a temporary problem. Why? Well, it can happen that there are 2 winners more or less at the same time, so that part of the network will believe in 3 and part of the network will believe in 4. So there is this fork that you can see in the picture. Right? But what about the next block? is it possible that 3 will be extended and 4 will be extended more or less at the same time again, right? Is it possible at all? Well, the point is that it is possible. Of course, it's only a matter of probabilities. And that's why if the puzzle would be very simple, in the sense that the puzzle is solved in 10 seconds, of course, you are going to have a huge number of forks and they all extend quickly. And this is extremely insecure. Why is it extremely insecure? Because once there is a fork, you are an honest miner. You have to decide either you mine on the left or you mine on the right, which means the computational power of each branch is reduced because we are not all mining on the same list. We are now splitting, okay? And when you are splitting the computational power of honest players, it's easier for the adversary to be the winner, to have on his own more power than others on a given branch, okay? So it's very important that forks are kind of rare. And how do you make them rare? It's, okay, after the fact, today I can say it's easy, but Nakamoto had managed to solve all these problems. So the rule is the following. If you run 100, if you check the 100-meter final at the Olympic game, you have 5 people arriving within 20 cents, right? If instead you look at the marathon, in between the first and the second, there are almost always 20 seconds, 40 seconds, or there is a huge delay where everything can go over the internet 10 times back and forth, right? Okay, so the idea of Nakamoto, so this proof of work must be like a marathon. So it's 10 minutes long on average. It's expected 10 minutes for the network to find a solution. So that like in the marathon, when there is a winner, there is enough gap before there is a second winner, so that the first block decided by the winner reaches almost everyone, and therefore there is no fork. You cannot exclude, of course, there is a small probability that there is a fork, right? But then this fork continues again, because after 3 or 4, you know, there will be 3 extended and 4 extended again at the same time. Okay, now it's getting very, very small probability. And that this can happen even 5 or 6 times consecutively, the probability now is extremely low and you can ignore. Okay? That's the idea why, because if instead only 4 is extended first, the longest chain rule means that everyone will join this unique chain 1, 2, 4, 5, okay, and 3 will be just a dead branch. Okay. So this is the intuition that actually, I mean, it has been. I'll have more arguments later, but it works extremely well. And in whatever I say, there is something I'm basically cheating. So far, I've mentioned in the above analysis, mentioning 5 or 6 blocks that you have to wait before being sure that you are on the right branch. Okay, basically I'm saying Amazon and the bank should not immediately provide the service when they see this block. They should wait that this block is deep enough in the chain, it's followed by 5, 6 more blocks. Okay, and only after that they should provide the service. So that this is the right branch, it will not disappear anymore, this transaction, so they really got the money. The reason why I'm cheating is that 5 or 6 blocks are actually satisfying if you are defeating natural forks. What is a natural fork? Just there are 2 winners, it happened, what can we do, right? So this is natural. But if instead it's the adversary attacking with his power in order to produce such double spending, for instance, then this analysis is extremely insufficient, okay? It's easy to see. Why? Take an adversary that has just 1/3 of the computational power. Well, I mean, it's still a lot, right? But it's below 1/2, right? 1/3. It can be 20% if you want, right? But still significant, but way far from majority. Okay, so the adversary is below majority a lot. Okay, so let's say 1/3. So what is the probability that while 4 develops honestly with more nodes, he also can develop 3 honestly at the same speed, generating winning blocks, more or less at the same time, right? If he has 1/3 of the computational power and the rest of the world has 2/3, right? So we have just half probability of finding probability half compared to the rest of the it is probability of succeeding is just half of the rest of the right probability, and therefore of doing it twice is 1/4. You see, 3 times in 1/8. Eventually, 1/2 to the 6 or to the 7 to the 8 to the 9 is not that small. It's not that small at all, right? So if you have a transaction and there is a lot of money there, if you are attacking some government with the ransomware, you want to be paid in Bitcoin for an equivalent of $1 billion, and they pay you, don't wait for 6 blocks, just 7 or 8 to release your data. You should wait for a few days to be sure, because a government could manage to set up something to revert your payment even way beyond 6 blocks. Okay, it's not approachable by regular people, this attack, but a government well motivated can do that if desired. Can do that, but still for a window that is limited. Indeed, I was saying 6 is insufficient against an adversary that can be, in this case, the government, that has 1/3 of the computation power. It's really a lot, right? So the reason we are all fine with 5 or 6 blocks in the real world with Bitcoin is because basically we believe that nobody's doing these games, or if somebody's doing it, it's doing it with 1% of the computation power, which is very, very low. Okay, that was something that I wanted to clarify, because basically this number 5, 6 looks like magic. It has an explanation, and it's a very good explanation, satisfying one for the natural forks. It's unsatisfying in case of an adversary that has a lot of computational power. Okay, in that case, don't see 5 or 6 is really very little. You should wait. Okay. Important thing, last comment of the slide is that you know why am I discussing in this first lecture about consensus? Because this is a decentralized computer that we are constructing, we are discussing, and then the target of the school will be about smart contracts. But basically, you write programs, right? When you write programs for a computer, you should not ignore how your computer works, right? Ignore its bad, terrible idea to ignore how it works. The existence of forks, if you are working and writing smart contracts for a forking blockchain, because not all blockchains fork, Bitcoin forks, you should be aware of this fact, because then there are many papers, there is research showing that then you get insecurity of your smart contracts because somebody can take advantage of forks, even a fork, even 2 blocks against the goal of the smart contract. Okay. All right, so it's very important to know the platform before using it to write programs. Okay, good. Okay, this is a comment here coming from the previous slide. You recall Nakamoto showed that the power of targeting liveness instead of consistency when things go wrong. For instance, it's very easy to have forks if there is a network attack, right? If there is a network attack and there is only Europe mining and then US mining, but there is no communication between Europe and US, you will have a fork, clearly, because Europe will go ahead with some blocks, US will go ahead with other blocks, right? So, so forks, you can have this problem, and Nakamoto decided not to penalize liveness. So as you can see, transactions are still added and added. Whoever is in Europe is adding this transaction in Europe, whoever is in the US is adding this transaction in the US. And if there is a fork, no network attack, but just forks for other reasons because of multiple winners, and you send transactions, most likely your transactions are in both branches. So you really have liveness, even with forks, right? There is no problem. What is the actual problem in case of attacks is the consistency, because for a while, which means for the length of the fork, you don't have agreement among the various nodes about what is the state of the blockchain, right? Because my last 3 blocks are different from your last 3 blocks. So consistency is under, when there are attacks, consistency is in trouble rather than liveness, okay? It's the opposite of what was happening permissionless setting for the case of the partially synchronous model that I was mentioned. Okay, that's a comment to see. So, okay, for the case of Bitcoin, essentially there is a block every 10 minutes that requires about 2 to the 70 hashes done by the entire network, with the difficulty is adjusted. And the idea, I discussed it already, the idea is to keep it as a marathon, right? So that you don't have many forks. All right, good. We are approaching the end of the second part. So let's try to wrap up. So Nakamoto consensus from proof of work achieves consistency and liveness, but with the caveat on consistency. Consistency is a bit in trouble. To have a transaction confirmed, so therefore to say this is the state of the computer, right? You should basically cut the last 5, 6 blocks, right? And then say this is the state, because the last 5 or 6 that you see are kind of unstable. They could disappear, okay? And this essentially means, as a consequence, that when there is a block added, the transaction, you have to wait about an hour to be sure that it will be permanently there. And this has impact on the applications. This number 5, 6 is just pure numbers thrown on the table. I gave you an example where I told you this number, instead of being 5, 6, should correspond to the number of blocks in 2 days if you want to play safe, right? So nobody has this number in the pocket. Essentially, the finality parameter is unspecified. It's basically on you to decide how much you want to make. Okay, and I explained this, the 100 meters race compared to marathon, right? The blocks should be slow in order to limit the forks. Okay, now important references to scientific papers, because many words, but okay, has anything been proved formally? Positive, the answer is positive. Okay, yes. So there is a fantastic paper on Pass et al. That proved that with just honest majority of computational power, okay, so you are fine with adversary at 49% of the computational power of the entire Bitcoin network. And whatever I'm saying, of course, it extends to similar blockchains that have proof of work plus longest chain. Right, these 2 main rules that are proposed by Nakamoto. There are many other blockchains that use these rules. So they are, let's say, Nakamoto-style blockchains. They have all these properties that they are secure with adversary below the 50% in terms of computational power. But wait a second, because there was an original paper of Garay et al. Managing to prove it for the synchronous model only. And then the paper of Pass managed to prove it for the synchronous models with bounded delay, but known bounded delay. This is not the partially synchronous model, okay? Okay. Notice that unlike in the permissionless setting, so in the permission setting, this bounded delay is equivalent to the synchronous setting. It means that instead of waiting 1 minute for rotating the leader, okay, because we have issues with the clocks, there is a bounded delay. Let's take the max bound. Okay, 1 hour. Okay, so whatever you do in the synchronous model can be done in this bounded delay model. Okay, in the permissioned setting, this is true. That's why I didn't even discuss it before. For the permissioned setting instead, because of these proofs of work, the 2 models are not equivalent. So it is actually a very important news that. Pass et al. Proved that even in the bounded delay model, even that requires you to know this bound, the consensus achieved by the Nakamoto consensus, it is secure, achieves consistency and liveness, but with these assumptions. Then there is also negative results. So Pass showed that if you consider the partially synchronous model, okay, you cannot, with the Nakamoto blockchain, have consistency and liveness, all right? So this essentially means that, and you can experiment it on your skin, right? you can always, even if you have money on the Bitcoin blockchain, you should always fear that your money will disappear, because tomorrow a longer chain appears that will cancel the moment in which you receive it. It can happen. Okay.
Even have a question
Yes.
about this result. What is the assumption about the adversary?
Yeah, the adversary
about computational power.
Just less than but the adversary should not have a majority, so up to 49.9% of the computational power.
Okay, thank you.
But as you can see, it doesn't reach the partially synchronous model, indeed, right? So the positive results are in the synchronous model, where even in the permissionless setting with the less strong protocol, as I mentioned, you get indeed just majority there, right? So the same here, you get majority in the synchronous, and synchronous with the more realistic synchronous with the delay, bounded delay. Okay? But already with partial synchronous, not only you don't get, you cannot have an adversary with just 49%, but even with less, you cannot. The point is that there is basically a lower bound. It's proved that you cannot have consistency aliveness, both properties, if there is this unknown delay of messages. Okay. This is proven in this paper. And okay, I guess it was proven mainly for Bitcoin, because then there is this other sequence of papers by Imraf Garden and others, that they show that this is inherent for a proof of work-based consensus. Okay, so the best you can get is what Pass proven. If you design a blockchain that is secure with proof of work-based consensus. Okay, this is what the researchers managed to do after the fact, because if you read Nakamoto's paper, I mean, the analysis, it's there is an intuition, but of why it makes sense. But then a lot has been done to prove it formally. We have positive results and there are also negative results. All right. Let me see what comes next. All right. So these are papers, right? From theory, kind of theory. Practice is good. So Bitcoin is validated in the sense that it's working. There is great health for Bitcoin. Ethereum has been also a proof of work blockchain, a Nakamoto blockchain, until a few days ago. Then there has been a switch to proof of stake. So they got rid of proof of work. But very important, Ethereum had some problems about reverting history, which means making inconsistent the content of the blockchain, right? Having this computer that becomes two computers. That's why there is Ethereum Classic now. But that inconsistency, I want to say, that problem that happened was not because of an attack. That problem was a governance, was decided basically by the honest miners to change the past, right? So kind of, if you believe in honest majority of miners, you should be fine if they agree on changing the past, because you believe it in them and they decide to do so, right? So you should be fine. So that's not really an attack. So that's why the Nakamoto consensus, I mean, is still good in practice, as long as the specific blockchain that you are considering has a lot of computational power, honest. Right? If there are many other, let's say, cryptocurrency with their own blockchains that also are proof of work blockchains, and you can wonder who is mining, how difficult it is. Okay, in those cases, I don't want even to comment. Okay. As you can expect, all these miners evaluating hash functions in order to add a new block and caching a reward are consuming a lot of energy. Okay. Already a few years ago, the energy was the equivalent of Czech Republic and sticks. There is dedicated hardware to do that. It doesn't make things better. I mean, they consume energy, but moreover, it's to build dedicated hardware. It's also a waste of resources because it can only do that. It doesn't do anything else, that hardware. Right? So that's a problem. some people say it's not really a big problem. I don't want to argue or go into details. I'm saying just it's a problem, big or not, it is a problem. It would be nice to get. Okay, let's have a recap on the innovations, the magic, fantastic innovations of Nakamoto. There are several. That's why it's a beautiful revolution that he started. So first of all, in the past, consistency was untouchable. Only liveness could be penalized. Nakamoto said, no, I have another idea. We give priority to liveness, and then the consistency, we will see later how to fix it. Okay, that's first idea. This is very, anti-intuitive, but in the end, it made complete sense. Second, great idea, the introduction of the proof of work. So, in the permissionless setting, the Byzantine leader can produce inconsistency because it generates two messages different and signs both of them. It's very cheap to do it. And Nakamoto made this cheating very difficult to do, because then in his context from Nakamoto, the adversary should produce two blocks. So good luck. You have to do mining in two blocks, right? So great idea. Fantastic idea. And number three, maybe it's even the best one, I would say. All previous papers, when I was mentioning the permission setting, academia researchers were just considering, okay, adversary can do polynomial time computation, will not break secret scheme because that requires exponential time computation, and nobody can do exponential time computation. That was the idea. Instead, Nakamoto changed the model of the adversary, because for Nakamoto, the adversary is not somebody that can do any polynomial time computation, because solving puzzles is also polynomial time computation. So the adversary can produce all blocks that he wants. Right? They said no, he has just less computations than honest players. So it's a fantastic idea, because then it showed you can build stuff on top of this. And this was completely underrated, this idea before. I mean, there was already something, but very, very little. Now there is actually this research done exploiting this idea, even beyond the blockchain ecosystem. And, so many beautiful ideas. The fact of realizing the system, also having game theoretic ideas inside, like having incentives, so that you can actually have concretely rational players as honest players, so that the adversary is then in trouble trying to defeat them. Okay, after the beautiful ideas, let's comment also some limitations, right? We are here to basically support science in general, not to support something in particular. Let's see what is not really ideal in Nakamoto consensus, right? I gave some concrete examples about Bitcoin because it's the mother of all blockchains and so on, and it's a Nakamoto blockchain, right? But whatever I said is actually much more generic. Transactions are considered confirmed after a long time and only probabilistically. You have never probability one that your transaction will not be removed. Okay, that's what's a limitation, right? You have to wait until a transaction is confirmed. Number two, waste of energy and resources because of the proof of work. It's bad for environment. Moreover, it can be an excuse for a country to say, look, this is illegal because you are polluting too much, right? So, and we know that countries, governments need those excuses to stop services sometimes. So that's not something to ignore. And the fact that a country can stop the mining activity affects decentralization, because now, then you have only part of the world that controls the blockchain, right? Proof of work are expensive and that they require incentives. That's also incentives. And this can be problematic because it's not clear how to establish a nice, good, stable incentive mechanism. Where do you pick the resources? So, I'm giving you Bitcoins. Okay, but what's the value of Bitcoin? Because in the market can go down, right? And you don't know what players could adversely do. Because you can suggest what the honest player will do, but there are papers like selfish mining showing that, look, there are maybe, the moment there are incentives, players try to maximize their revenue. So they can deviate from honest behavior in order to get more money, right? So this is a complicated. Moreover, the cost of energy, and we know it in particular nowadays, it's not the same everywhere in the world. Therefore, mining is not really fair. There are countries where mining is easier, and this affects decentralization. And finally, concentration of resources in mining pools might damage decentralization. Okay, this is more controversial. So we know that if you buy some dedicated hardware, most likely you are not going to do mining on your own, because it's very rare that you will actually mine a single block. Okay, so most likely you will join with your others in a mining pool, so that the mining pool will often collecting all the power to produce new blocks. You will get a fraction, a share of the right. So that's what people do. And some people criticize the existence of very few mining pools that have a large part of the computational power. I actually see it differently. I see the existence of mining pools as a positive thing, because it allows people also with limited hardware to join. So actually it helps in having more honest computational power. Second, also, I think it's positive because sometimes blockchains require some updates, right? And in order to make updates, people have to talk to each other. And if you have mining pools, you have the managers, the mining pools, so you have some well-specified actors to start talking to in order to organize and to prepare an update. So updates in Bitcoin, for instance, they take on average 4 years. So it's an extremely slow process where people have to get convinced, then they make an upgrade of the software after everyone had the chance to look at it, and there is large consensus off-chain, out of the Bitcoin blockchain concept. So actually, I don't see it as a big issue, these mining pools, but some complain about the issue of the concentration of computational power. All right, you survived to part 2. We can pause again. And okay, we are here for the third part of this first lecture. So the school of about Algorand Smart Contracts. This third part is about proof of stake and Algorand. A second, want to drink. All right. So when you are part of a system, usually you are not always there, right? You are sometimes online, sometimes offline. And when you return online, you would like to know what happened, right? It happens to all of us. We take a plane, right? During those hours, we don't have internet connection. And then after it, we start recovering everything that we missed. How does it work, right? You ask to somebody. And to whom? You should ask to people that were part of the system, because they know what happened, right? Yeah, that's what is it. How do we do? Yeah, that's a simple. We ask a few members of the community, in particular the ones that are okay. And to whom? If many people were there, how do you pick the ones you ask, right? You should ask the one that have better reputation, more visibility, because they are less likely to lie, right? And you ask not just to one person, you ask to more people, and then because still one person can cheat, can lie. But if more people, they all answer consistently, right? So then you are fine with the answer, and you are updated, right? All right, how do we translate the above natural solution to permissionless blockchain? So the fact that I go offline and I return, I would like to know what's the state of the system. Who are the visible actors, right? The visible actors in a blockchain, who knows? So it depends on the application. You don't know because it's an abstract concept. I mean, we don't know what is running on the blockchain, except that in the permissionless setting, somehow all blockchains are running with a cryptocurrency, because if there are computers running all around, some software to maintain it, there must be a reason, right? Some reasons could be just because it's of your interest, it's part of your business, but that would be really blockchain focused to do something specific. But if a blockchain is like even a general purpose, can do everything, right? Why are you spending energy to maintain it, right? So the kind of everyone is hoping for some form of revenue through cryptocurrency. It shouldn't come directly because of, for instance, of the mining. It can come because behind the blockchain there is a foundation that generated initially a huge amount of tokens and distributes the tokens along the way, or there was an ICO, you got part of the tokens, and now you are basically funding the ones that maintain the blockchain, or giving part of your resources. I mean, there can be several reasons why there is an underlying cryptocurrency, and actually permissionless blockchains, I mean, the ones that we have now practically that exist, they have it. And when you have a cryptocurrency, therefore you have wallets, you have owners of cryptocurrency. And they were there. The owners of cryptocurrency are the only people that for sure in all cryptocurrency, you can go and ask, please, what happened when I was not there, right? So you give a specific role to them. And the more stake, the more amount of cryptocurrency an entity has, the more reliable is his answer because he's interested in the good health of the blockchain, right? Because he has it has a large investment in it. And this kind of tells you that, okay, then when we want to resolve the consensus problem, right? Why are we going for crazy ideas when there are stakeholders that are interested in maintaining the blockchain? So go ahead and generate the next block. Let's find a way to maintain the blockchain through the help, in particular, of stakeholders. This is the idea that motivates proof of stake consensus. It's a supernatural idea. Indeed, what is kind of weird is that wasn't considered first because, and instead Nakamoto considered proof of work, right? Because with proof of work, it's very tricky. Even external people that have nothing to do with the content of the blockchain, that never appear, don't have a single unit of that cryptocurrency, they might buy some hardware and start mining, right? Okay, so this is the motivation. Proof of stake blockchain, we give to stakeholders the possibility of selecting blocks. Okay, interesting that came after proof of work because it seems even more natural. All right. So we understood in part 2 of this lecture a lot about proof of work. So now that we want to do something based on proof of stake, we should understand why. Let's compare. What are we trying to get? Why should it be better? Okay, so there are several specific things to observe. So first of all, if you are going for a proof of stake consensus, okay, then it's easier to leverage old school consensus. So Byzantine fault tolerant protocols. The one done for permission blockchain. Why? Because actually, if you look at the stake, basically at the way the cryptocurrency has been distributed among wallets, you have now the possibility of saying, okay, there is user number 1, user number 2, and user number 7,000. That's it. These are the players. So now they can run an old school consensus protocol, right? So that's interesting. It's something that on proof of work you cannot do. But with proof of stake, you can actually take advantage of nice results coming from many years, decades of research for the consensus problem in the permissionless setting. And they have identities. And of course, if they have a wallet, they have a secret key. So everything is there. There are signatures for free. Everything is fixed now, right? So you can leverage the best results, the one that we are using all this infrastructure. The assumption on honest majority changes a lot. For proof of work, there is this possession of hardware that can perform a lot of computations. While for proof of stake now, the assumption is about how much money you have. Essentially, money not out of the blockchain, inside the blockchain. Okay? The amount of cryptocurrency of the blockchain that you possess. Could be considered more realistic than hardware possession, but I don't know if it's true or not. Okay, so proof of stake. So we are going at some point to have a leader proposing a block. Let's be careful. A leader proposing a block in a proof of stake blockchain is not as anonymous as in the proof of work setting. precisely because in the proof of work setting, everyone can decide to be a miner. Today I start, I buy hardware and I start. Nothing about me is currently in the blockchain. And when I manage to mine, there will be my public key that can be a one-time public key. I will never use it again. It will appear just for me to cash the reward, right? So it's not, it's extremely privacy preserving, if you want. For proof of stake, the situation is different. Proof of stake, if you are a leader, you propose a block, you are that person that received that money 1 year ago for some reason, then spent in that other way, you know, your history is known. That's very important. It's a big difference. It's indeed, I mean, in this comment that this can, for instance, introduce risks of coercion. But if I know you, I know that you have a lot of stake, I can tell you that you should never add transaction coming from that person, for instance, to boycott somebody, right? So a criminal can announce, for instance, that whoever adds a transaction from a given public key will be attacked, right? So then, you know, if you propose a block, you never put, because you want peace, right? You don't want to be attacked by anybody. And I mean, the fact that you have a stake, kind of, because you use the stake, there is also kind of your name is also somewhat there, and you can be attacked. If you are the owner of some infrastructure, somebody can do a denial of service attack against your infrastructure. If it's a hotel that has a lot of stake, somebody can attack the website of the hotel, right? There are some proposals. It's not that inherently proof of stake blockchain is non-anonymous and subject to these attacks, but these proposals that exist, some papers published, they resolve even the problem nicely with fantastic tools, but it's completely unpractical, not efficient, and nothing that can be run currently and not soon. Okay, that's good to start in this way, and then now let's comment. Let's try to do this proof of stake consensus. Okay, so the stake is naturally represented by a public key, because it's your wallet, it's where the money is, and an amount, it's the current balance that you have on this wallet, right? And we don't start from scratch, we are not crazy. There is a fantastic theory coming from Nakamoto, we want to recycle it. We lacked very much, right, that lottery with scratch cards. Why not? Let's use it. And then the question is, how do I implement a lottery in the proof of stake setting? How do I have a ticket that is like a scratch card, but I don't do a proof of work? It's with proof of stake, right? And notice, I mean, if the adversary is not very rich, he will not have many tickets, right? And therefore will not win often. That's why the damage that we can do is limited. Okay, let's see, how can we do such a lot? How can we run such a lot? Okay, ideally, if I have n units of cryptocurrency, for now I'm generic on proof of stake. At some point I will discuss in particular Algorand. For now I'm discussing a generic proof of stake based blockchain. If I have n units of cryptocurrency, you know, if I want to run, participate in the lottery, I have a right to participate n times, right? Every unit, one ticket, right? So I should be able to run a function with my computer or my smartphone, whatever. Eval with argument 1, eval with argument 2, eval with last parameter n, okay? That should be possible. Eval should be determined, I mean, it's useful that if eval is really deterministic, okay? Because why? Because if it's not deterministic, then I can run eval multiple times with input 1, multiple times with input 2, and then it corresponds to multiple tickets. No, but I want one ticket for one ticket for 2, right? So that's the reason why eval should be deterministic. The output of eval should look random. Why? Well, you recall the puzzle, the Nakamoto puzzle was trying to find an X such that when you evaluate SHA-256, you get a string where the first 70 bits are 0. Okay, that's the way the puzzle is realized in the Nakamoto blockchain. So even if eval has an output that looks random, you can apply the same idea. You can say, okay, you have scratched your card and you won the lottery. if the output of eval has the first 70 bit equal to 0, or 30 or 50. I mean, these are parameters, but that's the idea why it will be useful if the output of eval is essentially looks random. Okay, then next, eval should be run by the stakeholder because this is my ticket, right? It's not that somebody is able to run the lottery with my tickets. My ticket, I scratch my cards, you scratch your cards, right? So therefore, the secret key associated to my wallet should be also a parameter of eval. And the result of eval, the fact that I won, that the last 70 bits in the output of the first are all zeros, should be publicly verifiable, because then I announce that I won, and I want everyone to be able to check, right? With the puzzle, the check was just a hash and check that the output is all zero. But with eval, how the others are going to check? Because they cannot also evaluate eval. Why? As I just said 1 minute ago, for eval as an input, I'll have to put my secret key. So others will not be able to rerun eval with my inputs, of course, because I want to keep my secret key hidden. All right, so interesting to realize a lottery based on the proof of stake rather than proof of work. You need some ideas. It's not this. There are some complications, but fortunately, for some reason, in 1999, Silvio Micali, the Italian Turing Award winner, Michael Rabin, that is another one, and not Italian, but still, and Salil Badan published a paper where they proposed a tool called Verifiable Random Function. I open a window, a parenthesis, and then I close it. So the motivation had nothing to do with the tickets of the lottery, okay? So it was for other reasons, in particular, probably to try to replace in some applications the random oracles and so on that I mentioned. But it was not really about lotteries. There is nothing there about that. It has been, fortunately, the killer application was found later, fortunately, even though, I mean, I remember even some papers on mine, I used this tool, but it was not really a disrupting tool until proof of stake needed it. Okay, let's see how it works, okay? What is a verifiable random function? It's actually a family of algorithms. Here there are 4 algorithms. The first algorithm on input as a unity parameter generates, that is a key length essentially, represents a key length, generates a pair of keys, public key and secret key. Okay? Then there is an evaluation function. As I was telling you, I'm trying to be compatible with what I was promising here, right? There will be a secret key to evaluate. So there is a secret key, and then there is a message to evaluate. That could be this I, in the number 1, 2, 3, it's this I that is here. Plus I'm concatenating it to the previous block because I'm playing, I'm generating a scratch card for the next block to win the next lot, right? This is basically the previous block is an identifier of which lottery I'm trying to win. And there is an output, right? It's a sequence of bits, capital R. All right, as I told you, I cannot send my inputs to others because the secret key is secret by definition. So others, to check, will have to do something else. I have another algorithm called the proof generation algorithm, gem proof, that still requires my secret key and the same input, but will provide an additional string that we call proof. Okay? What the rest of the world will do to check that actually associated to my public key and evaluating with the correct input because I have such units of stake and corresponding to this lottery, prev block, okay? This specific lottery, because there are many, every block has a lottery, right? Everyone can check that the procedure verify, taking as input the announced output are, and the proof, the additional, the auxiliary outputs 1, okay? This is the verification that others will do to actually confirm that I won the lottery. Okay? So this is, I didn't tell you how we can construct a verifiable random function. I'm just telling you this is the way it's formally defined in terms of algorithms. These are the inputs that should be provided, and these are the outputs. Okay, all algorithms should be fast because otherwise we waste time, right? Gen key can be a bit slow because normally you don't generate keys all the time, right? So, but the rest, eval, gen proof, verify should be fast. So R should look random, and I told you before why, like, we want that also. This is a security property of the verifiable random function. We want that it should be hard, infeasible, to find even a fake key, basically a public key that you don't get through gen key, but you get it through some crazy procedure if you're an adversary. Right? The adversary can do whatever he wants. So you cannot generate a fake key such that later on you can basically cheat the verifiers, providing R, a pair R proof, but also a pair R prime different than R. Both that can be both verified. Okay, you should not be able to do it because this means that you are able to generate more tickets basically with the same unit of stake. Right. So verify, you see, it takes as input my public key, number 7, my 7th unit of stake, the previous block. That's it. I can announce only 1 R because if I can announce 2 R, 3 R, I have more chances to win. I'm cheating, right? So that's why it should not be possible for anybody, even with a fake public key, to have multiple R's and proofs that gets verified correctly. Okay. Said so. Now the question is, how do, I mean, this is crazy cryptography. It's we need a cryptography lecture about this stuff to understand it, or it's simple. It's simple actually. There is a very simple construction that I can show you here because it's absolutely trivial. So for this key generation algorithm, right? So we start with the signature scheme, any. Okay, the standard ones, except that they have a specific property to be unique signature schemes, so that basically signature schemes that have deterministic signatures. Okay, perfect. So there is a gen key procedure for the signature scheme, a unique, an algorithm to sign, and an algorithm to verify. And essentially, what I'm saying here, it's not completely correct because you must also make sure that any key that you generate, the security requirement that was mentioned before, doesn't allow you to have multiple outputs. But for simplicity, let's overlook it for now. So the key generation of the verifiable random function will just be the key generation of this signature scheme. Okay, so basically, when I generate a PK and CK, here are a pair of keys for a signature scheme that is unique. Basically, the signature function is deterministic. That's it. Then there is an eval procedure. There must be, right? If I'm constructing, what do I do in this eval procedure? Where I need to provide this output bar, right? How do I compute it? I just compute a signature with the underlying signature scheme, right? Signature will give me a string. Then I give the string in inputs to H, that is a hash function that we consider as a random oracle. Okay? So notice that you can understand now, a signature, nobody knows what will be a signature because only the owner of the secret key can compute a signature, right? So nobody knows what will be this signature. The signature might not be random, might have several bits equal to 1 or 0, but I give it something that nobody knows. I give it an input to the random oracle. Okay, so nobody knew it. I give it to the random oracle. Now you get an output that is random, right? So that's why it works nicely, this eval procedure. What is the proof? Nothing special to do. Just the same. Okay, this is a typo here. It's again the same signature that I used here, an input to H. It's the output of gen proof. Okay. So now to verify this verify procedure that will want to make sure that this pair R proof comes really from the eval function. Okay. This verify procedure will just verify the signature. Okay. Recall proof is just a signature, so it's the natural verification of a signature, and we check that R is actually H of the signature, which is true. Okay, so this essentially means that verifiable random function comes kind of for free if you have a signature scheme with some specific special properties. Okay, so nothing crazy. they existed already, these signature schemes, so nobody had to construct them on purpose to realize verifiable random functions. Because in this framework, I'm using H as a random oracle, and there is no problem to do it because they are used everywhere. Right? The original paper on verifiable random function of Mikhail Rabin and Saddam actually didn't want to use random oracle, so had them more complicated. Because their target was actually to replace random oracle in applications. So they couldn't use random oracle in the construction. But for this type of application that we have in mind now, that is proof of stake, where we are realizing the lottery to evaluations of a verifiable random function, we are perfectly fine using also random oracles wherever they connect. Okay, so what I discussed now is the following. You recall the consensus through proof of work and the longest chain, right? Was part 2 of this lecture. Good. There were issues with that proof of work. In particular, one issue was the energy consumption, right? Good. With this idea, since the proof of work was realizing a lottery, with this idea of verifiable random functions, you can replace the proof of work with the proof of stake. So you can realize again a lottery, and the adversary in the proof of work case didn't have enough computational power to dominate the production of blocks. In this case, instead, the adversary doesn't have enough money and to dominate the production of blocks, because money in the blockchain means cryptocurrency possession, and that drives through the VRF the lottery and the tickets that you get. Okay? So through this idea, we should now have already how everything works, right? Because just a replacement proof of work with proof of stake, the rest untouched. Okay? With some issue that I discussed here, not to forget, of course, when they were here. Yeah, I mentioned a few things not to forget, but there are differences, right? Okay, so indeed, let's see if we make this replacement, where do we go? Which results do we get? Right, oh, we have now something better for the environment, and this is fair, kind of fair, right? Now, if we really stay with the previous approach, with Nakamoto's approach of using the longest chain rule and forks and so on, because it's a lottery, there can be multiple winners, right? And you have to resolve the problem, and we resolved it with longest chain. You can do that. There is this blockchain called Cardano with the consensus algorithm that is based on proof of stake that applies the longest chain rule. Therefore, there are also forks, and it works, so it doesn't waste too much energy. But since there are forks, there is still this slow finality, in the sense that when you have a transaction that appears, it's still a temporary transaction. You have to wait before considering it finalized in the blockchain. Okay? Instead, one can also look at different directions. Indeed, I mentioned it before. Look, once you are in the proof of stake setting, you can take advantage of Byzantine software. And that's precisely what Algorand decided to do. Indeed, if you take the above approach about running the lottery, and you not only select the winner of the lottery as a block proposer, but you also select a committee. A committee means the governance of a permissionless blockchain. Those nodes, the nodes that participate in the BFT protocol. Okay? That is the old school where identities must be fixed, the number of people involved is fixed, kind of fixed under some bounds. Okay. Okay, indeed, this is the idea of Algorand that is completely different. Therefore, does not apply the longest chain rule. If there are conflicting winners of the lottery, so more blocks have been proposed, Algorand, for now, these blocks are not yet added to the blockchain. There will be this Byzantine fault tolerance protocol that will be used to approve only one of them. And this one will be added to the chain. This means that once a block is added, it's confirmed permanently. There is no way that it will be reverted. And this is fast finality, because as soon as you see it, because it has been added, you can consider the transaction as non-reversible. Okay, very good. These two directions. Then there will be, additional discussions specific on Algorand. Let me now say that there are still very important things to discuss. There are some issues that are not applicable to proof of work that instead are part of the proof of stake setting. For instance, there is nothing at stake attack. What is this attack? Well, if there is a fork, it's not the case of Algorand, for instance, the case of Cardano. If there is a fork, there are multiple branches. Since it's cheap to evaluate a VRF, a variable random function, you have no reason not to basically participate in the lotteries that are in all branches. So basically, all branches keep going and going, nothing stops, right? Instead, with proof of work, you have limited hardware. So if whatever you don't put on the left branch, whatever you put in the left branch in terms of power, you are removing it from the work that you could have done on the right branch when there is a fork, right? So this does not apply to proof of work, but it applies to proof of stake. So there are forks, no reason for people to invest in one direction only. They can continue, let all the possible branches grow, right? That's a problem. Second problem, long-range attack. What is long-range attack? Is the following attack. I don't have more than, I have only 10% of the money, let's say, okay? But you know what? Now I cannot attack because I have too little money. But current, basically, stake holders, the ones that have a lot of money, okay, in their wallets, will spend it at some point, right, in the future. After they have spent it, right? What's the problem for them to give me their secret key? In particular, I can pay them to give to me their secret keys, right? Once I have their secret keys, I can go back in time when that stake was majority of those people, and now I have the secret keys. So I can now start a branch from the past, and I have all the secret keys because I bought them paying cheap money, because I paid when there was nothing anymore in the wallets. And I can quickly, there is no proof of work, I can quickly generate now another long branch, right? Or can create an equivalent and an inconsistent version, right? And what will people, right? This is called long-range attack. It also does not apply to proof of work blockchain, because if you go back in the past, in the proof of work blockchain, you have to mine more blocks. It's a disaster. But with the long-range attack in proof of stake, it is actually an issue. Liveness issue. I am a stake owner, right? I have some money, small amounts, as many others. I like to play with some smart contracts. That's the reason why I have it. Why should I now be part of this crazy consensus and run this function and do the work of a validator of the blockchain to produce a block? I have no idea. I don't want to consume electricity. I have the battery of my smartphone or whatever. So this also, it's also an issue. It's a liveness issue because, well, it's not only that, it's at least liveness, but it's a liveness issue mainly. It can expand, but it's for sure. Because basically the blockchain can stop because nobody is anymore participating to the consensus, because what is the incentive to participate, right? Adaptive corruption. A winner of the lottery will can then say, I won the lottery. Somebody has money to give to me in order to prepare a block that has some specific things that he likes. I will do it and I take it, right? So there is this possibility that one could be corrupted before producing before announcing the transactions that we do. All right. All these issues. So proof of stake, this is just say, okay, it resolves the electricity problem, but it doesn't come for free. There are a sequence of issues that didn't apply to the proof of work setting, and now they must solve them if you want such system. Okay. Okay, good. And now we go to blockchain that will be used for smart contracts in this tool, Algorand, right? It is a proof of stake blockchain. So we'll discuss more in details how all these steps are realized in Algorand. There are a few papers, mainly these 3 papers that try to specify all the details. All right, so let's see. Okay, let's go step by step. Let me see also on the Q&A if there is anything. Okay, I think also because time is passing fast, and I will actually postpone answering to questions to the end of the lecture. Okay, so we have a verifiable random function, and it is used in order to select the block proposer, right? Like the lottery. Okay, nothing changed. Okay, I'm just confirming. Of course, there can be more than one winner. It's natural. And in Algorand, there is also an associated priority. So basically, I have a winning ticket. Somebody can have a winning ticket that is more winning than mine. Okay, perfect. And also, the verifiable random function is used to select. So there is basically another lottery. It's to select a committee with hundreds or even thousands of members. Okay? So you are a winner, but not a winner of in sense of proposing a block, in sense of being then part of the committee. Okay. In Algorand, in particular, this use of the VRF to select a block proposer and to select the committee is called the cryptographic sortition. So a bit deviating from the term lottery. Okay. Perfect. But the idea is essentially that, but you can see it indeed as a cryptographic sortition. They're just picking some names from the ballot box. Okay. So what happened is that once there are some block proposers, so even more than one proposer circulates, there is an execution of a Byzantine fault-tolerant protocol among the committee members. Okay, they will decide which block to approve. So the priority is used because the initial input of every player in this protocol will be precisely the block with the highest priority. Okay, perfect. Okay, so everything is fine, everything works, right? I mean, once they approve, what it means that they approve, they sign, right? Well, this is my output, I signed it, there is a majority that will sign it. Okay, so the rest of the world can be happy with this block. It's a block that is added because it's supported by a large majority in the community. Okay, liveness requires attention. Recall what is liveness. Liveness is the following property. I am a user of the system. I send a transaction. Will this transaction appear and when? Right? Will a block appear including my transaction? Requires attention. Indeed, if you don't have a large participation to the consensus, okay, there will be no block created at all. Okay, and it can happen because many people decide to switch off their smartphone or computer, so they are not evaluating the random function. So they are not proposing blocks, they are not joining the committee. Adversaries can try to do whatever they want, but adversaries are limited. So they will appear in the committees as a limited number of members. And therefore, their support for a block is limited and insufficient because there are very few of them, right? Yeah, indeed, this is also written here. The Byzantine agreement protocol will have too few participants and the required threshold of votes for a block will not be reached. Okay, so keep in mind, this is something extremely important. Large participation is required from stakeholders. Okay? If you have stake, you should participate. It's assumed that you are honest, and as honest, you have your other smartphone or whatever you want running in the software to participate in the consensus. Okay, security is proven formally, okay, in these papers, with the adversary below the 1/3 threshold. Okay, we know that Silvio Micali is the original proposer of this system. He also had the possibility of crucially relying on his previous results, like verifiable random functions. But also, I want to say that after him, when basically they collected enough money to hire people, extremely strong cryptographers joined the team, in addition to Synchronous. Okay, good. So that was the high-level overview of how it works. Let's now comment, right? So consistency is maintained, so even in case of long asynchronous periods, okay? As long as they are followed by some shorter synchronous period where the network is not under attack, okay? It's essentially the partially synchronous model, and therefore Algorand can be considered secure in the partially synchronous model, unlike Bitcoin. Okay, that's an additional. It's something not to discuss. Anyway, it's a mathematical proof in a model. It's theory, but it's better to have it rather not to have it. Fork, I mean, when we say forks are impossible, actually they are not impossible, but they can be extremely unlikely depending on the parameters. So given selection of parameters announced several times by the Algorand team, basically gives probability of a fork less than 10 to the 18. Well, 1 over 10 to the 18, sorry, it's a clear type, of course, 1 over 10 to the 18. And basically, this is, it means it's less than the number of seconds from the Big Bang, which means if you have every second a block, you have to wait billions of years before there is a single fork. In current implementation of the blockchain, a block is added every few seconds, so it's super fast so far, and liveness is not guaranteed during asynchronous periods, I would say. Okay, it follows the original paradigm of the old school consensus, where when there is a problem with the network, with synchronicity, you want to keep consistency. So no fork, fine, but no liveness guarantee. Okay, now another point, very important. The adversary, he has less than 1/3 of the money, okay? But there is a committee of restricted, so you can just corrupt them with this money, that is less than 1/3 of the total, but still it's enough money to corrupt people. We can corrupt all of them, right? And then therefore it's always the adversary that decides the next block, because there are block proposers. There can be 25 blocks proposed, and there is this committee selecting one. If the committee is bribed by the adversary, could always pick out of those 25, do one of the adversary, and there is always one of the adversary because he has 1/3 of the threshold. So if 25 blocks are proposed, 7, 8 of them come from the adversary, right? So there is look, how do they solve it? And the idea to solve it, it's actually extremely brilliant. The point is that the adversary doesn't know the identity of the committee. This is extremely brilliant. So they have inside Algorand a Byzantine fault tolerant protocol where every round is played basically by different subcommittees. So if you're a member of the committee, you play once, you don't play several times. Because the moment you play, it means your message is propagated, and then you are subject to corruption, right? But when the moment you are subject to corruption, you played already. So you corrupt me, but I'm not going to play anymore because others will play the next rounds. Wow, that's a very brilliant idea. It's called player replaceability. That is actually, it's kind of essential. Right? I mean, if you believe that to these attacks where the adversary could corrupt with his limited money, will still corrupt the committee so that its blocks are picked. Okay. Basically, this makes these adaptive attacks where the adversary on the fly tries to see which place can be corrupted and join him, makes them much less effective because they are really difficult to mount. Now that it's the fact that, I mean, it's always too late. When he knows that somebody is in the committee, it's too late. Okay, and here it's written in the slide. And these steps where the subcommittee changes are repeated until actually the agreement is reached on it. All right. Okay, now there is also a specific word that has been used many times. It's like it's a proof of stake protocol. We can say it's a pure proof of stake protocol. What is this pure word? Where does it come from? It's because in the environment of proof of stake consensus, there are some variations. Some variations actually They still use verifiable random function, but for instance, not everyone can join the consensus. There are only some delegated people, for instance, in some proposals. In other proposals, instead, in order to participate in the consensus, you have to freeze your money. Once you freeze it, in the sense that you cannot touch it for smart contracts or whatever, it's there for a while to participate in the consensus. Yeah, so there is this requirement. So Algorand doesn't have these limitations. So in some sense, for Algorand, the participation is easy because you don't need dedicated hardware. You don't need to risk, put your money frozen somewhere, and you are not discriminated in the sense that you have not been selected in the set of dedicated people, but everyone can participate. So these all features have been kind of defined like pure proof of stake, to mean that the others are not pure. Okay. All right. So kind of we can say that Algorand consensus achieves decentralization because everyone can participate, right? Security because that probability of fork is extremely low, and there is a mathematical proof that the system achieves also consistency and the liveness. Scalability. What does it mean here? So, and therefore this has been various times been proposed as a trilemma solver, because you get the three properties together that was something in kind of very hard to get. So this is true, but scalability here, it means that everyone can participate in the consensus. Even a large number of people can participate in the consensus. Nobody is out. And still the consensus is efficient. That's why it's scalable. Okay, here I have an important remark. With scalability, it's therefore about participation in the consensus, that it scales. Right? Another story is instead the scalability of a blockchain, because there are many transactions and these transactions take time to verify. Right? Because you add in the set of in the sequence of transactions only the valid ones. You don't add trash junk in the blockchain, right? So you have to verify transactions. So validating transactions can be extremely expensive depending on the complexity of the smart contracts, and it can require a lot of computational power, right? So that's another story. To have scalability in the sense that there is a huge demand, many transactions come. Is your blockchain able to include all of them? Okay, that is not related to consensus. So trilemma does not apply to that. Trilemma can apply to that. You can define the trilemma in that direction also, but then Algorand is not a trilemma solver, right? Because, at least I didn't discuss any reason why it's easy to verify transactions. If transactions are complicated, they are not easy to verify, right? But that is something else. I had the blockchain stack in one of my first slides in part one. That is work for the scalability layer, right? So we give it to someone else. In this lecture is about consensus, so we can skip this problem. That is a beautiful problem, very interesting. There is a lot of research in this direction, but in Algorand and Alpha. The fact that in general transactions could be expensive to run and verify remains a scalability use. Okay, that's exactly what I just said. Perfect. Let's move forward. All right, so now there is an important point. I was mentioning before, really I have to, since I am a stakeholder, I have one algo, I have 7 algos. Really I have to be online all the time and consume electricity with the current cost of electricity in order to provide my service to the system, because there is no reward here, okay, for participating in the consensus. There is no reward. Or why should I do it? Moreover, I want to tell you more. Not only I consume resources, but having always my secret key online, okay, online in the sense that it's computing, it's in my device and it's computing. So if my device at any time for even a small time window is under attack, my secret key can be read by the attacker and he can take my money, right? So it's a bit scary, this fact that I have to use the secret key all the time helping the consensus. So actually, this security issue it's like two issues, right? Why should I really do it all the time? And second, it's also a security issue. So the security issue is actually resolved completely because a stakeholder can generate a temporary participation key that can be used to sign a batch that it can be even millions of ephemeral keys. And then that participation key can be deleted. Of course, before deleting it, you have to associate this participation key to your accounts that everyone in the world, they will recognize that your participation to the consensus is legitimate because you have stake. Okay? But this participation key cannot be used to spend your money. So that's why on my smartphone, I can have this process running all the time because it's a key that cannot spend my money. Nobody can take my money. It's just participation in the consensus. Yeah, and I can keep my secret key in cold storage, super safe place, and I take it only when I need to spend money. Each ephemeral key is used only for one round of the consensus, only for one block, basically, and can be deleted after it. All these, I deleted it. Why do I do it? Okay, the extra spender key is the one that is in smart contract is not used in the consensus. Okay, why am I deleting the keys, participation and ephemeral keys? Well, to mitigate those attacks, I mentioned you two attacks, right? One was the nothing at stake attack that was about the forks, but it doesn't fork Algorand. The other one was long range attack, where an adversary eventually will get somehow corrupting or through a leak from devices, will get the secret keys of players and will go back in the past and use them for a fork for generate some inconsistency, right? Well, if keys are deleted all the time, this participation ephemeral keys, the adversary will not find this material. Okay, that's very important. Okay, these activities are performed by so-called participation nodes, which means whoever participates in the consensus, and everyone should participate in order for the consensus to go through. Everyone means, a large percentage. In the Algorand blockchain, there are also relay nodes. These relay nodes are special nodes. They are actually hubs useful for the efficiency of the system. So if we have now a block every few seconds, it's also because of this relay node, nodes, right? Exactly. But this is an important remark. So far, at least as far as I know, currently they are still centralized. I mean, this means that if you want to have to run a relay node, you have to call Algorand and have an agreement with them, right? So it's kind of centralized. But there is a goal, and there is also a program, I think, to move towards decentralized permission relay nodes, but that's for the future. All right, so this kind of completes my description with pros and cons of this system that you are going to use to develop smart contracts in the next lectures. Here I have in the last slides the references that I mentioned in my slides. So whoever is interested in knowing more, how does it really work, this Byzantine broadcast and so on, okay, go and check the DS93 paper. How does the impossibility work? And you can go there, or the verifiable random function, whatever, right? Everything I mentioned here with the reference, you can find here the name of the paper, and you can investigate whatever you find that you think is more interesting for what you are doing. And that's all. This completes my lecture. I am glad you survived. Bye-bye.